Thanks. Okay, everybody. I'm glad to see there's so many of you here since we're competing directly with the PFAS session, which is kind of a challenge. I put a little bit of PFAS in the end of my talk to try to make up for that, but I don't know that that was enough to make any difference to the equation. So can we put up my slides? Is this me? There we go. Okay, so I'm Paul Tratnyek. I'm at Oregon Health and Science University. I'm pretty much the only person responsible for the content of this talk, although I added a couple of recent collaborators informally listed on the front page there, Michelle Shear, Rick Johnson, and Drew Latta, because we're working closely together on some projects right now that relate to this, although they haven't seen any of the slides I'm presenting today. I started putting this talk together by adapting a couple of other talks that I've given in past years that relate to the question of chemical oxidation and reduction broadly. And one of the slides that I remembered and decided to use at the very beginning here was the slide that I developed for the Science Advisory Board meeting when I was defending a about to be funded CERTA proposal about maybe 10 years or so ago. That was really about the idea of core concepts that were overarchingly relevant to the question of chemical oxidation and reduction in environmental conditions. And so I started out that slide with this rather bold statement that is almost all approaches to remediation by contaminant degradation involve oxidation reduction reactions, almost all of them. And I said this tentatively the first time, and I never got any pushback on this, interestingly. My little cartoon that's in the upper corner here was to emphasize that point. Obviously, ISCO and ISCR are fundamentally oxidation reduction processes. Abiotic natural attenuation, aerobic biodegradation, anaerobic biodegradation are largely redox processes. The only one that you might argue that's significant that really maybe doesn't sound obviously like redox is in situ thermal. But even then, when you talk to those vendors, they usually invoke some sort of redox-related contaminant degradation processes. So I figured that statement was fair. In terms of oxidations defined broadly, I meant to include not only aerobic biodegradation processes in general, but particularly ISCO processes. And conversely, with respect to reduction, same thing. Anaerobic biodegradation processes in general, but ISCR processes specifically. And then I wanted to emphasize the theme that there is some complementarity between these things, certainly at a fundamental level, right? Oxidation reduction, they're mirror images of one another in many respects. And also from a remedy point of view, there are some complementary aspects, and sometimes you see vendors to advocate using them in combinations or in sequences. And I'm not really going to have time to dig into that as much as I had planned to, but to just a placeholder for that, I used at the bottom right of this figure slide a figure that I found from an old poster, 2013, from then the FMC folks, where they were basically describing the criteria that you might use to decide between using ISCO or ISCR on a particular site. So then the other previous talk that I was channeling as I was beginning to prepare this was this one here. It's called New Tools for Managing Chlorinated Solvents Sites, and I gave this at the 2018 CERTA Symposium meeting, and it's my all-time favorite presentation, and thankfully I've got it recorded, and so you can find it on YouTube, and if you either search it on my YouTube channel or look for my group website, you can find it that way. And there's a recording of this presentation there, and it's kind of distinctive. It's a little different than this one and most others, and so I recommend it to you. But the reason I brought that up is that one of the things that I did in that presentation is I classified a bunch of important ideas in the remediation realm as tools. And one of the things I classified as a tool, as a technology, is a family of technologies, is ISCO. And to make the talk fit into the time limit, I had to condense ISCO to basically one slide, which is what I'm doing here. In this slide, I'm at the same time giving emphasis to the fact that ISCO is not new. It's been well established for a long time. And to illustrate that, you can see in the dates that are listed over here on the left side, how long ago some of the seminal defining publications or other kinds of developments came out. So Dick Brown was patenting a Fenton-based groundwater treatment process in 1984, and then Watts and Siegrist were working on those processes in the mid-1990s, and permanganate was already a thing in the mid-1990s, and persulfate even dates back all the way to the 2000s. And so there's really nothing new about ISCO for the purposes of this presentation today. And in fact, the term ISCO has been widely used for a long time. And just to illustrate that, I'm using this cover from the book that Bob Siegrist edited in 2011. That was a assertive book that was basically had all the big players writing chapters and all kinds of comprehensive coverage of the key concepts. What I want to contrast that to is in situ chemical reduction, which is not exactly new anymore either, but it's much more new and it's much more in flux in terms of definitions and scope, et cetera. And the slide that I developed a couple talks ago to lead into this is shown here, where, again, to mirror on the previous slide, I documented what I believe are some of the key earliest examples of ISCR as it's currently being known. And so there's two clusters of sort of parallel efforts that date the beginning of this. The first one there is really revolved around a product that was trademarked by then FMC and was described in some publications by Jan Dolfing and Alan Seach and John Vogan and Jim Mueller, where they use the term in situ chemical reduction, but in a way that's a little bit different than the way we're using it here. And they don't currently promote that formulation as such. The second one was really Dick Brown. And so Dick Brown organized a bunch of symposia, Battelle meetings, and over a series of years, and really pushed this idea that there was a concept called in situ chemical reduction, which was of general significance, and that and that's the angle that I'm going to take. I got drawn into it by Dick Brown around 2010, and in 2014, I teamed up with him to write a book chapter where we put some effort into coming up with something akin to a definitive definition of what we meant by ISCR going forward, and this is what we came up with. So the idea was to be inclusive and fair and balanced to the extent that we could, but also be more precise and systematic about how we make a definition. So the first bullet says, in general, ISCR refers to a category of in situ groundwater remediation technologies where treatment occurs primarily by chemical reduction of contaminants. So the emphasis there would be on chemical and also on primarily, and that's a hedge to allow for the fact that, as emphasized in the second bullet and illustrated on the little cartoon in the upper right, we're acutely conscious of the fact that a lot of in situ chemical reduction processes are closely coupled to the microbiology. And so the microbiology generates the reducing conditions, which ultimately generates the reducing mineralogy, which is responsible for what's on the blue arrow on the far right side of that figure, which is what we call ISCR. So it's not to the exclusion of the microbiology, it's closely coupled, and I'll develop that a little bit further in the next couple of slides. I also tried to include in this definition that these in situ chemical reduction processes could be intrinsic natural processes, so not necessarily involving engineered interventions, or they could include sort of biostimulated in situ conditions, or more directly, more aggressively engineered conditions. All of that in principle fits under the scope of ISCR the way I like to define it. So I kind of already introduced that idea that we have two types of reductants that we're concerned with here, the intrinsic ones and the engineered ones. And that was really playing off of again, Dick Brown's early contributions to this. And he used to use this goofy cartoon on the right side of this figure to emphasize the idea that ISCR had two branches, or two legs, if you will, the ZVI one and the DVI one. And so that corresponds roughly to the engineered reductants, that's the ZVI. There's no natural ZVI of any relevance. And the intrinsic ones, which would include DVI, divalent iron, which of course occurs biogenically in other ways, but it could also be stimulated chemically. In recent versions of this slide, I've added a third bullet at the bottom, and I'm still playing around with this. I haven't fully developed this idea, but it fits my theme for today pretty well. Question is, do we really need, maybe we need another branch. Maybe we need another branch for activated reductants. So I'm playing off here the analogy to ISCO. So most ISCO technologies, except for permanganate, don't really operate as a direct chemical oxidation. They operate as an indirect chemical oxidation where you have an oxidant that's activated to produce a reactive species, and that's what actually degrades the contaminant. Same thing may apply, it does apply to some degree in the reduction case, but that concept is not very well developed in this field yet, and I'm kind of building towards seeing more of that. Okay, so among the intrinsic reductants, I should elaborate a little bit on what they are. This slide was actually formulated, this text was actually formulated for that book chapter, which was a good number of years ago. Things have shifted quite a bit, as I'm going to get to in just a second. But at the time, we were mostly focused on minerals, stable minerals that you can buy or look up in a mineralogy textbook. Things like magnetite, green rust, clays that contain iron 2, iron oxides with adsorbed iron 2. It's known that those things are thermodynamically reducing, and that's illustrated in this redox ladder here. Redox couples that are clustered here are pretty low on that redox ladder, and they're strong enough reductants to reduce a variety of contaminants. This could say the same thing about the second bullet, the iron sulfides. So they contain reduced sulfur. The reduced sulfur is a potential reductant, and there are a variety of mineral phases that are relevant there. Pyrite is the stable one that sometimes comes to mind, but mckinnowite is probably the more relevant one. It's the more freshly precipitated, more reactive one, and that's actually a segue into the theme that I'm going to start to build on here. And that is that in the way we imagine this stuff taking place in the environment, all these processes are closely coupled together, and they're coupled to the microbiology. And so this cartoon that's on the right side of this figure was drawn by, I think, Pat Evans and then distributed by Erica Beckvar, or some combination of them. And you've probably seen it before. It's in some AFSI reports and reproduced in other places. And it summarizes different ways in which the in situ microbiology might generate reducing conditions that result in what we're calling ISCR. So apparently abiotic reduction of contaminants. And I don't have time to go through them all in detail, but the one on the upper left is just ferrous iron adsorbing to iron oxides. The one on the upper right is magnetite with iron 2 absorbed on it, both reducing TCE on the surface of the mineral. And the two below are an in situ iron sulfide phase and an in situ green rust phase generated on the surfaces. And there are a variety of relevant features that go along with this, including that we've subsequently learned that these indirectly abiotic reduction processes generally prefer reductive elimination of chlorinated solvents, which tends to avoid the stall intermediate problem, which I'll get to in just a second. So now, but there's a new twist here, and so to illustrate that, I've been using this cartoon recently. It summarizes, similar to the previous slide, but there's some slightly different elements of going on here. So in the upper left of this figure, we've got the microbiology, and the microbiology is doing two things here. It's reducing the minerals to form reducing mineral phases. It can be producing these more reactive mineral phases like, say, green rust. Or it could be reducing the contaminants directly. That's the vertical arrow over here on the left side. But there's another aspect to this here, which is that the primary mineralogy, which is what I emphasized in those couple of previous slides, like magnetite, can be undergoing transformations in situ, which may be biogenic or somewhat abiotic, to form secondary phases that are more reactive. And so this is not really an entirely new concept, but we've given it a different name because we're giving it a different emphasis, and we're calling it RMIs, which stands for reactive mineral intermediates. And I'm going to elaborate on that just in a second to help justify that. But I would point out before I go there that the implication here is that this diagonal green arrow from this corner here down to there is our hypothesis is that one's not generally the most important thing. So that would be, say, magnetite directly reducing TCE. Our hypothesis is that what usually really happens is that biology and mineralogy generates these reactive mineral intermediate phases, which aren't just magnetite. And those are the things that are primarily responsible for the abiotic natural attenuation that you see. All right, so the RMI hypothesis, so reactive mineral intermediates. This is the bullets on the left side of this slide are the same as I've used in a few recent talks. I've condensed the evidence from my sphere for this RMI hypothesis into those little screenshots on the right side. So the RMI hypothesis is that we have active precipitation processes going on in situ that generate phases that are metastable, and therefore they're reactive, and they become reactive mineral intermediate phases, and they're intermediates because they're transient, because they're formed and they're degraded. And so this has a number of key characteristics. The first bullet in the middle there, they're authogenic, they're formed in situ, but they're transient. So if you turn off the formation process, they go away. That means you can't collect a core sample necessarily, and send it off to your favorite analytical lab and expect that what they measure in their lab 2 weeks later is representative of the RMI phase that I'm hypothesizing is mainly responsible for abiotic NA of TCE. There are a couple other more subtle corollaries to this. This one here is that what goes along with this idea of a transient character is that the lifetime of the RMI phase is actually short. It doesn't last very long by itself. It has to be continuously formed and degraded. And that results in a steady state concentration if the conditions are balanced. And the steady state concentration can be very low. That's okay. A lot of people make the mistake of assuming that because the steady state concentration of the reactive intermediate is low, it can't be important. That's not true. If the reactive intermediate is very reactive with the target contaminant and it's steady state, it doesn't go away, it's continuously reformed, you can still get a lot of net reaction. And so I don't have time to elaborate on the four figures on the right. We've published a variety of papers where we've shown these are all lab-based experimental data of various sorts showing evidence for this reactive mineral intermediate being a key part of or a dominant part of the transformation process. More recently, there's been a couple of interesting developments that are not the same as my RMI hypothesis. In fact, they didn't really even know about or acknowledge our RMI hypothesis, but they're parallel and they're synergistic and they're supporting, so I'm happy to see them. One of them is shown here, maybe I should point this way once in a while. Over here is a series of papers by Lisa Axe's group that on what they're referring to in the title, it says reactive iron mineral coatings. She doesn't give it an acronym type name for this, but these papers are emphasizing this theme. And the whole series of these papers is about the idea that there are these reactive iron mineral coatings in these in situ environments that are hard to characterize and important. And most of her work has really been focused on the characterization aspect, not so much on the contaminant degradation aspect. But it's very synergistic with what I'm telling you. The other one on the right is from Stefan Pfeiffer and Andreas Kapler and others in Germany. And they're coming at this from a much more sort of purely biogeochemistry point of view, not really contaminant driven so much at all. But they are also focusing on this idea that there are reactive transient phases of these iron minerals under environmental conditions. They call them RAMPs, reactive redox active mineral phases. And so their RAMP hypothesis is very analogous to ours, except again, just somewhat of a different focus. So that helps to support our argument. Okay, so now switching to engineered systems, there are lots of chemical reductants that you might add that are nominally stronger than the natural intrinsic ones. And the obvious one is zero-valent iron. And that's used in a whole bunch of different established technologies. At this point, I listed some acronyms. You can test yourself and see whether you can translate them all. There are also some other zero-valent metals that are relevant, and they're much less common, but I'll elaborate on a couple of those just in a second. I listed divalent iron here again because there are some remedies where people directly add, say, chelated iron 2, and so that would be engineered. It's not a super strong reductant in the way that ZVI might be considered, but if it's there, there's various ways that people add sulfide, again, sort of a chemical addition of sulfide. In particular, the distinctively anthropogenic one would be calcium polysulfide-based foam, which is a fairly well-established approach. There's a whole bunch of different approaches that involved injecting dithionite. Originally, the original one was called in situ redox manipulation to generate in situ iron 2. So the dithionite part of it is a purely engineered reductant addition. There's some techniques that involve adding hydrogen with catalysts, and there's some others. I point out that in this redox ladder here, I've added a few things to it. The iron couples are over here on the right side, and these are metals that you might want to remediate by reduction, and these are chlorinated or organics you might want to remediate by reduction. And these are chemical oxidants over here on the left side. And the reason I put this particular figure here was just to point out that although there are a number of well-known primary ISCO-type oxidants that plot quite high on this graph, up in that gray zone, which is above the water stability field, there's only one reductant, that's ZVI. And so it kind of looks from here like this, that somehow oxidation is generally more amenable to stronger treatments than reduction. So, why did we get so excited about ZVI as a strong reductant? Well, if you think back about what people had in their minds when this first started, the idea was that ZVI was thermodynamically a stronger reductant. Therefore, it's going to drive dechlorination of, say, PCE down through those hydrogenolysis steps to more complete dechlorination, and thereby get past the Stahl intermediate problem. So this would be PCE, TCE, there's the Stahl intermediates. And these arrows that connect them here are the hydrogenolysis steps. Those are the ones that are usually seen in biodegradation, right? And of course, it tends to slow down a lot, and it stalls here. And the idea would be that if you just push it harder, if the reductant's stronger, it would push it deeper in through that sequence. And the same thing applies for the chlorinated methanes over here too, via chloroform, dichloromethane, et cetera. Exactly analogous issue. Sorry. Turns out that wasn't what was going on at all, right? As you all know, that the ZVI doesn't really push the reaction through these hydrogenolysis steps. It makes an end run around the Stahl intermediates via the reductive elimination pathway. And that's a peculiar characteristic of ZVI that turns out to be really important. Now, you can make an argument that a stronger reductant would favor a 2-electron reduction over a 1-electron reduction. As an academic, I can do that. But it's not immediately obvious that was going to be the case. But we now know that is the case. And this slide I put in here just to kind of push that theme just one step a little bit further with an example of an extremely recalcitrant chlorinated solvent, trichloropropane. So in the red in the middle is 1,2,3-trichloropropane. We had a CERTA project to work on that a while back. We were struggling to get ZVI to dechlorinate it, and we got really desperate. We decided to hit it with an even stronger reductant, and so we ended up with zinc. And what I'm confessing to you now is that when we first decided to pull zinc off the shelf, we had the same mentality that we had in the old days. We thought, zinc, it's an even stronger reductant. It's just going to push that dechlorination further. What we subsequently learned was that's not what happened at all. What happened was that the zinc resulted in pretty facile reductive elimination of TCE, and then that process was fast thereafter. So we didn't make the hydrogenolysis go faster. We made the reductive elimination go faster. And so you can see on this redox ladder here, probably you can't really read it, but you can see the dot, which is right there is zinc. There's iron, there's zinc. So you can see now the zinc is, in terms of being millivolts more strongly reducing than the water stability field, it's about comparable to those to the primary ISCO oxidants. But there's more to this. So these guys way up here that I've introduced on this version of the plot are the reactive intermediates in ISCO oxidation. So that's hydroxyl radical and sulfate radical. So thermodynamically, they're way up here. So if you make them, they provide even more driving force for oxidation. Is there an analog to reduction? Well, if you go down to the bottom of this figure down here, I got a couple more dots that I just added in this version. So there is titanium, aluminum, and magnesium. And so magnesium is way down there. So it's actually, from a thermodynamic point of view, it's even more millivolts reducing than the strongest radical oxidants are oxidizing. So that's pretty interesting, pretty promising, right? And so there are some papers on treatment of contaminants with zero-valent magnesium. But it never really took off. They've been around circulating kind of in the low level for a while, but it never really took off because there was really no need for it. And so nobody went there. So more recently, it dawned on me that the one unique characteristic of zero-valent magnesium is that it's so low that you can't quite see it there, but there's two dots there. There's two points in that curve. One of them is the magnesium. The other one is reduction of water to solvated electrons. And so magnesium can form solvated electrons. So that's the ultimate reductant from a thermodynamic point of view. And so that gets me to nearly to the end here. That gets me to this. So what about using solvated electrons as the supercharged in situ chemical reductant? And that idea is not the least bit new either. Most of you probably don't remember, but I do. The idea of using forming solvated electrons by a number of different sort of high-tech methods for water treatment has been around for a long time. And so the most compelling way I could think of to prove that to you is this cover of a book edited by Bill Cooper and others, published in 1998. And notice that on the cover, there's a solvated electron. Right? That the whole thing was about that. And not so many years after that, they had a truck driving around Southern California that had some sort of corona discharge type thing or electric arc type device that generated solvated electrons that they were using to treat MTBE in groundwater in Southern California. But of course, MTBE wasn't that big of a problem. It didn't really justify that, so it went away. So we haven't heard about it since then. But of course, you all know that recently, PFAS has become everybody's number one concern, and there's a whole bunch of technologies now that are getting a lot of attention and seem to be getting traction and success and publications that use a number of different methods of generating solvated electrons to defluorinate PFAS. Right? And so I just used to illustrate this, I used one of the graphic abstract arts from one of the papers by the group at UC Riverside. And the key thing to see there is that there's a PFAS, the fluorines are in yellow, and see those little scissors? The scissors are meant to show what they're calling HF exchange, but that's reductive defluorination of the fluorine groups. So it's clear that you can do defluorination of PFAS with solvated electrons. So my theme here is that the realm of in situ reduction has got room to grow, right? So if you let me absorb that into in situ reduction, there's a whole lot of new things to do and directions to go with this. So by way of summary and discussion here, just the first part here was introduction to remediation by in situ redox processes defined broadly. So the point being that the biotic and abiotic processes are coupled. That's what's illustrated in that cartoon in the upper right. Fundamentally, they can be complementary. As remedies, they can be used in practice in combinations of both alternatives, but also in combinations. I didn't really get to develop that in this particular talk, but hopefully in some future talk I will. The RMI, or ramp hypothesis, if you will, is the middle main point of this presentation. We're arguing that these reactive phases are going to be the dominant thing in these, particularly in the abiotic natural attenuation context, and probably that applies to the engineered ISCR type scenarios too. And at the end, the idea that there are extreme oxidants, you already know about those, hydroxyl radical, sulfate radical, and there's an analog in the reductant realm, and the magnesium itself might qualify for that, but the real poster child for that, I predict, is going to become solvated electrons as we go forward. So that I'll finish by just acknowledging that almost all the funding for this work has come from CERTIP, so they deserve almost all the credit. A little bit of funding has come from organizations like NSF, Department of Energy, and there's a bunch of people that have been important players in this. I'm featuring only those that are kind of most relevant to today's theme in this audience. So Damin Fan, who was a PhD student with me a while back that worked on this very stuff, and is now at Geosyntec. Ali Salter-Blanc, when she was a student way back with me a long time ago, working on trichloropropane, and is now at Jacobs. Michelle Shearer, when she was a student with me a long time ago, is now a professor at University of Iowa. Tiffany Torralba-Sanchez, who worked on PFAS with me and is now at Much Associates. And Rick Johnson, my long-term colleague at OHSU, who's now the Dean of the School of Public Health. So with that, I will stop, and I don't know how much time I have, but I'll take questions if there is some.